Have you ever, stopped to think about why your hot coffee eventually cools down or how a fridge manages to keep things cold?
Or even the really big questions like where the universe is ultimately heading.
Exactly. Believe it or not, these things, they seem totally different, but they're all connected by one, well, foundational idea. Okay, let's unpack this.
Mm.
Today, we're diving into thermodynamics.
Yeah, it's a field that really underpins so much. Everyday stuff, cosmic scale stuff, you name it.
And what's really great, I think, is that it's not just some dry, abstract science term, is it?
Not at all. It's actually a profound framework for understanding energy, how it transforms, and maybe most importantly, the direction things naturally take.
The direction.
Yeah, pretty much everything that happens around us, it's universal. Applies from tiny interactions in a cell all the way up to, well, how stars work.
Right. So you've sent us the Wikipedia entry on thermodynamics. Our mission today to distill the core ideas, find those surprising bits, and hopefully give you those aha moments, so you feel really informed without getting bogged down in all the math.
Sounds good. Where should we start? The definition.
Let's do that. The big picture first. What is thermodynamics fundamentally?
Okay. So at its heart, thermodynamics is the branch of physics dealing with heat, work, and temperature.
Right.
And crucially, how they all relate to energy, this thing called entropy we'll get into, and the physical properties of matter and radiation. It's really the science of energy in motion and transformation.
And you mentioned its reach. It goes way beyond just physics labs, doesn't it?
Oh, absolutely. To really get the scope, you find thermodynamics woven into, well, physical chemistry, biochemistry, pretty much all engineering disciplines, especially chemical and mechanical, even meteorology, how weather systems work, and yeah, theoretical stuff too, like black holes, quantum physics. It's like a universal language for energy.
But here's something I found really interesting, kind of a twist. This super broad universal field, it didn't start with philosophers pondering the universe.
No, not at all. It started with something very practical, almost gritty, you could say.
Which was?
It's deeply rooted in the Industrial Revolution, specifically this burning desire to make early steam engines more efficient.
Ah, the steam engine. Okay.
Think about the context, early 19th century.
Right.
Nations competing. There was this French physicist, Sadi Carnot, back in 1824. He was absolutely convinced that engine efficiency wasn't just about engineering.
What else was it?
National security. He thought it was key to France's military and economic power, especially after the Napoleonic Wars. His work on heat engines, it basically kick-started thermodynamics as we know it.
Wow. So a military motivation almost.
In a way, yeah. But the groundwork, the actual seeds, were planted much earlier. People were just curious about how things worked.
So it wasn't just Carnot having a sudden flash of genius. It built up over time.
Precisely. You had figures like Robert Boyle way back in the 17th century. He worked with Robert Hooke, built an air pump, studied how gases behave under pressure. That led to Boyle's law.
Right, PVK and all that.
Exactly. And Dennis Papin, who worked with Boyle, he even came up with an idea for a piston and cylinder engine using steam, kind of hinting at the power source to come. Then later, you get Joseph Black developing crucial ideas like heat capacity, how much heat something can hold, and latent heat, the heat absorbed or released when something changes state, like ice melting.
Okay, those sound important for steam.
Hugely important.
Yeah.
And then James Watt comes along and makes a massive improvement to steam engine efficiency with his separate condenser. So all these pieces, driven by curiosity and practical need, they just set the stage.
It's amazing. Scientists piecing together universal laws, not just for knowledge's sake, but to win wars and build better machines.
Yeah, the practical driver was huge.
And even the name, right, thermodynamics, it tells the story itself.
It does. Comes from ancient Greek, thermes for heat and dynamis for power. Heat power.
Heat power makes sense.
And it was William Thomson, who became Lord Kelvin, and William Rankine, who really formalized using that term around 1854, specifically for the science of heat engines.
Okay, so that's the origin story. Let's get into the core principles. You mentioned laws.
Yes. At its absolute core, thermodynamics is built on four incredibly solid, universally true laws. Think of them as the fundamental rule book.
The rules for energy, heat, entropy.
Exactly. They form the axiomatic basis. Everything else in thermodynamics kind of flows from these four laws.
Okay, let's take them one by one. And the first one is, wait, it's called the zeroth law. That sounds odd. Why zero?
It is a bit strange, isn't it? It's called the zeroth law because its fundamental importance, especially for defining temperature, wasn't fully grasped until after the first, second, and third laws were already named and established.
Ah, okay. So they kind of retrofitted it.
Sort of, yeah. Because they realized it was so fundamental, it's the basis for even having a consistent idea of temperature.
So what does it say?
It states, if two systems are each in thermal equilibrium with a third system, then they are also in thermal equilibrium with each other.
Explain that a bit more. Thermal equilibrium means same temperature.
Basically, yes. If system A is the same temperature as system C, and system B is also the same temperature as system C.
Then A and B must be the same temperature as each other.
Exactly. Even if A and B aren't touching. Think about a thermometer that's system C. If it reads the same for your coffee, A, and your soup, B, then the coffee and soup are at the same temperature.
So it justifies using thermometers. Makes sense why it's fundamental.
It underpins our whole ability to measure temperature reliably. Without it, hot and cold would be completely subjective and chaotic.
Okay, Zeroff law establishes temperature and equilibrium. Got it. What about the first law? Does that get into energy itself? Like, can we create it, destroy it?
Right. This brings us to probably the most famous principle. The first law is essentially the conservation of energy.
Ah, okay. Energy can't be created or destroyed.
Exactly. It states, energy can be transformed from one form to another, but it cannot be created or destroyed. It's always accounted for, just moved around or changed form.
So in an equation form.
For a closed system, where no matter comes in or out, the change in the system's internal energy, we call that delta U, is equal to the heat, Q, supplied to the system, minus the work, W, done by the system.
So E equals QW.
That's the one. Heat added increases internal energy. Work done by the system decreases it.
Like if I push a big rock, I'm doing work using my internal energy from, I don't know, breakfast.
Precisely. Your internal energy decreases because you did work. And that energy came from the chemical energy in your food, which ultimately came from the sun, and so on. It's a chain.
Never created, never destroyed.
Never. And a really cool example from the source materials, opening a bottle of champagne or sparkling wine.
Oh, yeah. How does that show the first law?
When you pop the cork, the pressure inside drops suddenly. The gas inside expands rapidly, doing work on the surroundings.
Okay.
That work has to come from somewhere. It comes from the internal energy of the gas itself. So the internal energy drops, which means its temperature plummets.
Ah, and that's why you sometimes see that little cloud of condensation or ice crystals.
Exactly. The temperature drops so fast it freezes the moisture in the air right there. That's E, U equal QW in action. Work done by the gas, W is positive, leads to a drop in internal energy. It is negative.
That's a great visual. And this law also means no perpetual motion machines.
Correct. Perpetual motion machines of the first kind machines that create energy from nothing are absolutely impossible according to the first law. You can't get free energy.
Okay, first law, energy is conserved. Now, the second law, this is where things get a bit more philosophical. You mentioned entropy and direction.
That's right. The second law is where things get really interesting and sometimes a bit counterintuitive. It introduces this idea of irreversibility, the arrow of time in a sense.
The arrow of time. Okay.
Yeah.
How?
Well, a classic, simple statement of it is, heat does not spontaneously flow from a colder body to a hotter body.
Right. My cold coffee doesn't suddenly boil itself using heat from the cool air around it.
Never happens spontaneously. But the deeper concept here is entropy.
Entropy, the measure of disorder. Is that right?
That's a common way to think about it, yes. More formally, entropy is a quantity that describes the direction a system can evolve. It quantifies the state of order, or rather, the lack of it, the disorder or randomness.
And what does the second law say about entropy?
It says that in any isolated system, one that doesn't exchange energy or matter with its surroundings, the total entropy can only increase over time, or stay the same in ideal cases. It naturally moves towards a state of maximum entropy, which is equilibrium.
So things naturally tend toward messiness, disorder.
In a way, yes. Think about shuffling a deck of cards. It's easy to go from ordered, new deck, to disordered, shuffled. It's statistically highly unlikely you'd shuffle a random deck and have it come out perfectly ordered by suit and number.
You can't unscramble an egg.
Exactly. Or unrust metal, or unmix cream from your coffee. These processes have a natural direction, dictated by the increase in entropy. That's irreversibility, driven by the second law.
Fascinating. So first law says you can't win, get free energy. Second law says you can't even break even. You always lose some useful energy to entropy.
That's a great way to put it. You always increase the overall disorder or entropy of the universe with any real process.
Okay. What about the third law? You mentioned it sets a limit.
It does. The third law deals with the absolute bottom limit of temperature. It states, as the temperature of a system approaches absolute zero, all processes cease, and the entropy of the system approaches a minimum value.
Absolute zero. That's like super cold, right?
The coldest possible temperature, it's negative 273.15 degrees Celsius, or negative 459.67 degrees Fahrenheit. On the Kelvin scale, it's simply 0 K.
And what happens there according to the third law?
As you get incredibly close to 0 K, the entropy of a perfect crystal approaches zero. All the random thermal motion essentially stops. The system is in its most ordered, lowest energy state.
Can we actually reach absolute zero?
That's the kicker. The third law also implies that it's physically impossible to reach absolute zero in any finite number of steps or processes. You can get incredibly close fractions of a billionth of a degree above it, but you can never actually hit 0 K.
An unreachable limit. Wow. Okay, so those are the four pillars. Zeroth defines temperature. First conserves energy. Second dictates direction via entropy. And third sets the absolute zero limit.
That's a great summary. They form the foundation.
So, knowing these laws, how do scientists actually apply them? How do they study these things in the real world or the lab? It must start with defining what you're looking at.
Absolutely. A key concept is defining the thermodynamic system. This is just the specific part of the universe you're interested in studying. It could be anything.
Like my coffee cup again.
Could be your coffee cup, could be a car engine, a single cell, the Earth's atmosphere, anything. Everything else in the universe is then called the surroundings.
And the line between them?
That's the boundary. And the nature of the boundary is really important because it determines what can pass between the system and surroundings.
What kinds of boundaries are there?
They can be physical, like the metal walls of an engine cylinder. They can be fixed in place or movable, like the piston inside that cylinder. They can even be imaginary, just a defined region in space.
Okay. And what crosses the boundary define the system?
We classify systems based on that. An open system can exchange both mass and energy, like heat and work, with its surroundings. Think of a pot of boiling water without a lid steam. Mass escapes. Heat goes in and out.
Right.
A closed system can exchange energy, heat, and work, but not mass. Like a sealed pressure cooker. Energy goes in and out, but the water stays inside.
Got it.
And finally, an isolated system cannot exchange anything. No mass, no heat, no work with its surroundings. This is more of an ideal concept, like a perfect thermos bottle. But it's crucial for theoretical ideas like the universe as a whole, often considered isolated.
Okay. Open, closed, isolated. Makes sense. So within these systems, things are happening, changing, until they settle down. You mentioned equilibrium.
Exactly. When all the properties within the system, temperature, pressure, etc., stop changing over time, we say it's reached thermodynamic equilibrium. It's stable.
But the interesting stuff often happens when things aren't stable, right? When they're changing.
That's where thermodynamic processes come in. A process describes how a system evolves from one equilibrium state to another. Pushing the piston in your engine example, that's a process. Heating water, that's a process.
And are there specific kinds of processes scientists focus on?
Yes. Often it's useful to study processes where one property is held constant, as it simplifies the analysis. For example, an isothermal process happens at constant temperature. An isobaric process happens at constant pressure.
Okay.
An isochoric process happens at constant volume. And an adiabatic process happens with no heat exchange with the surroundings at all, like the rapid expansion of gas in that champagne bottle example.
Adiabatic. No heat transfer. Got it. So how do we actually, measure and control these things? What are the tools?
Well, the obvious tools are instruments, meters, thermometers for temperature, barometers or pressure gauges for pressure, calorimeters to measure heat changes, which helps define internal energy.
Standard lab equipment.
Pretty much. But another really important concept, especially for controlling conditions, is the thermodynamic reservoir.
Reservoir, like a big tank of something.
Kind of, but on a massive scale.
Sure.
A reservoir is a system so large that its key properties, like temperature or pressure, don't noticeably change when it interacts with your much smaller system of interest.
Can you give an example?
Sure. Think of the Earth's atmosphere. It's a huge pressure reservoir. If you release a small amount of gas from a container, the atmospheric pressure doesn't really change, right?
Right, negligible effect.
Or a large lake or the ocean can act as a temperature reservoir for something like a power plant discharging heat. The ocean's temperature barely budges. These reservoirs let us impose specific conditions, like constant temperature or pressure, on the system we're studying.
Okay, that makes sense. Reservoirs provide stability. Now let's go a bit deeper. If we're really dissecting this, we need to understand how energy transfer is precisely measured. You mentioned conjugate variables and potentials. Sounds a bit advanced.
They are a bit more abstract, but they're really powerful tools. Let's start with conjugate variables. Think about doing work. Usually it involves some kind of force causing some kind of displacement, right?
Like pushing a box, force times distance.
Exactly. Thermodynamics generalizes this. Conjugate variables are pairs of properties where one acts like a generalized force and the other like a generalized displacement. Their product represents energy transferred.
Okay, like what pairs?
The most common mechanical pair is pressure, the force, and volume, the displacement, or change in volume. Pressure times change in volume gives you mechanical work.
P times delta V. Yeah.
For thermal energy transfer, the pair is temperature, kind of like the driving force for heat, and entropy, the displacement related to how heat spreads.
Temperature and entropy. Okay.
And if matter is being exchanged, like in chemical reactions, the pair is chemical potential, the driving force for moving molecules, and the particle number, how many molecules moved.
So these pairs give us a precise way to track different kinds of energy transfer: mechanical, thermal, chemical.
Exactly. It's like detailed bookkeeping for energy.
Okay, that clarifies conjugate variables. What about thermodynamic potentials? What are they measuring? Stored energy.
That's a good way to think about it. Thermodynamic potentials are different ways to quantify the total stored energy within a system, but they're each defined under specific constraints, like constant temperature or constant pressure.
Can you measure them directly, like temperature?
Not directly with a meter, no, but you can calculate them from measurable properties, and they are incredibly useful.
Useful.
They help determine whether a process will happen spontaneously and what the equilibrium conditions will be under those specific constraints. Different potentials are useful in different situations.
Like which ones?
Well, there's the basic internal energy. Then there's enthalpy H, which is useful for constant pressure processes, common in chemistry. There's Helmholtz free energy, FRA, good for constant volume and temperature. And maybe the most famous, Gibbs free energy, G.
Gibbs free energy. I've heard of that in chemistry.
Yes. It's extremely useful for predicting if a chemical reaction will happen spontaneously under constant temperature and pressure, the conditions you usually have on a lab bench or in a living organism. If the change in Gibbs energy, delta G, is negative, the reaction tends to proceed on its own.
So these potentials are like mathematical tools for predicting system behavior under specific conditions.
Precisely. They let scientists understand and predict complex energy transformations in a very rigorous way.
Okay, this is fascinating, but it's easy to get lost in the theory. Let's bring it back. How does all this impact us? Where do we see thermodynamics in the real world, beyond the obvious engines and fridges?
Oh, the applications are incredibly vast. If we connect back to that bigger picture, it's moved far beyond just steam engines.
Right.
Think about atmospheric thermodynamics. Understanding hurricanes, weather patterns, climate modeling, that's all heavily based on thermodynamic principles governing air masses, heat transfer, and water vapor.
Okay, weather. What else?
Biological thermodynamics. How do living cells manage energy? How do they maintain intricate order despite the second law telling us things tend towards disorder? How does energy flow through ecosystems? That's all thermodynamics applied to life.
Life fighting entropy. Interesting.
Then there's chemical thermodynamics, which is fundamental to all of chemistry, predicting reaction spontaneity, calculating yields, designing industrial processes, developing new materials, drug discovery. It's everywhere.
And you mentioned some more exotic stuff earlier, black holes?
Yeah, surprisingly, the laws of thermodynamics seem to apply even to black holes. There's a whole field of black hole thermodynamics relating properties like mass and surface area to thermodynamic concepts like temperature and entropy. It's a deep connection between gravity, quantum mechanics, and thermodynamics.
That's mind-bending.
And there are newer frontiers, too. Quantum thermodynamics studies these laws at the scale of individual atoms and quantum systems. Thermoeconomics even tries to apply thermodynamic principles to understand economic systems and resource flows.
Wow. So it really is everywhere, from designing a better chemical plant to pondering the nature of black holes.
Its reach is truly immense. It's quite something.
It really is a testament to the power of these few fundamental laws, isn't it?
Yep.
That they can describe microscopic interactions in our bodies and the grand scale dynamics of the cosmos.
Absolutely. So to sort of wrap up the key takeaways for you listening, you've now got a solid grounding in what thermodynamics is, how it grew out of very practical engineering needs.
Right, the steam engines and Carnot.
The profound meaning behind those four laws. It's especially entropy and the direction of time, and how scientists actually model and understand energy using concepts like systems, states, and potentials.
It provides the toolkit, really.
It provides the essential toolkit for understanding energy across just about every scientific and engineering field you can think of.
So whether you're prepping for a meeting or just trying to get your head around a complex topic, or maybe you're just deeply curious, hopefully this deep dive has given you that shortcut, helped you feel genuinely informed, maybe armed you with some surprising facts and those aha moments.
Absolutely.
And thinking about those laws, it does raise a final kind of provocative thought for you to ponder. If the second law tells us that the entropy of an isolated system, like maybe the universe itself, always increases,
Always heading towards maximum disorder.
what does that imply for the ultimate fate of everything? Are we heading towards the so-called heat death of the universe, a state where all energy is perfectly evenly distributed, totally uniform temperature, maximum entropy?
And because there are no temperature differences, no further work can be done. Everything just stops.
The heat death paradox, is that where it's all inevitably going?
That's definitely something to ponder on your next walk. A big question flowing directly from these laws.
Indeed. Well, thank you for joining us on this deep dive into the truly fascinating world of thermodynamics.